Hey there, and welcome to the second video, the second lesson on our unit on Introduction to Derivatives. In the first lesson, we introduced the concept of the derivative as an instantaneous rate of change with the limit definition of the derivative, which works out to be the slope of the tangent line. So what we're seeing here in our next lesson, where we're going to be talking about we're going to see a little bit of notation stuff. We're going to see an alternate form of the limit definition of the derivative, and we're going to look at what the derivative would be kind of algebraically, graphically, and symbolically. And what you're seeing here in the first opening paragraph of your notes, it's telling you there are two main concepts in calculus known as the tangent line problem, which are specifically related to derivatives, and the area problem, which we will get into later, called integrals. Both of these are founded, they have their big ideas related to limits. In the previous lesson, we applied the difference quotient to a function, y is equal to some function f, and found the general slope formula. This calculated the slope of the tangent line at any point on the curve, provided the limit exists at that point. So this next bit here, this is something that I probably should have highlighted, but for some reason I didn't highlight it. Let me go ahead and pick a highlighter here. Let's go ahead and try and stick with the yellow color. Yellow. All right. And here where it's saying the general slope formula is also a function called the derivative function. What you need to start getting into your heads, what you need to start thinking of, is that the derivative is a slope. It is a slope of a tangent line at that point to a curve. So whenever you start hearing the term derivative or slope of the tangent line, they are interchangeable, very much like other things in algebra that you've seen, such as like roots, solutions, zeros, things like that for describing where the solution of a function would lie. And at the bottom here it says, here you're starting to get into the notation where they're looking right here at the notation where it says f of x or f prime of x. That f prime of x is what we would look at as our notation to indicate the derivative of a function f at some point. And at the bottom, a function that has a derivative at a point is said to be differentiable at that point, which is definitely something we need to make sure that we're paying attention to, because if I don't have a derivative, then the function that it came from couldn't be differentiable at that point. And there's going to be times when you're going to see that functions simply aren't capable of taking a derivative at a point. But today we're just kind of still broaching the idea of what it is. So here, this is where we're kind of taking a look at, this is your limit definition of the derivative. This is what you saw in your last video, in your last set of notes. One thing that I may want to add here is that, again, just to kind of emphasize, this is the slope of a tangent line. The slope of the tangent line, the derivative of the function, they are the same thing. So please kind of keep that in mind as we go through the lesson and in future lessons on derivatives. Here, what you're seeing on this page or on this section of your notes, this is just different ways of that we use for notating a derivative in calculus. The most common one probably is the one at the top where we say f prime of x. Depending on what we're looking at, maybe we might use y instead of f of x, so the derivative of the function would be indicated as y prime. dy dx is a very common way of showing that we're going to take a derivative. We're saying the derivative of y with respect to x, and df dx is basically the same thing as dy dx, but you don't really see that too often. And d dx of f of x is, again, the same thing. We're taking the derivative of the function at some value x. So just be aware, these are all different ways of notating a derivative of a function in some way. Now here what it's showing you is that, and I know the pictures that I have here on the slide don't match up with your notes. I'm adding this stuff here just for the sake of making sure I'm being thorough. Graphically, the derivative of a function at a point is the slope of the tangent line. That's kind of the big idea that we're talking about with derivatives. So all I'm showing you in the first picture here is the blue line here, because now that I look at it, it shows that we have two blue lines. The line that I'm talking about is this line here. This is your tangent line. It's tangent to the curve at point A. So that is the derivative of the function at point A. The next one that we would look at is kind of a numerical approach. And here it's just kind of walking you through. The picture itself is just kind of looking at the limit definition of the derivative. But numerically, this is where we're going to use that formula to kind of figure out what the derivative is going to be. And then here verbally, a function f is said to be differentiable at a point A and f of A if and only if it has a defined slope at x is equal to a, which kind of makes sense because we have to have something tangent there. We have to have that slope. If a function does not have a tangent at a specific point, then the function cannot have a slope there either. So that is what the verbal explanation is going to be. And I just kind of want to point out this here, if and only if this right here, referring back to things that you would have done in geometry, that would be known as a biconditional statement. So let's move on and see what we're going to be looking at, how it's going to be applied. So this first one here is asking you the example, the limit process of the derivative, or use the limit process of the derivative, meaning the limit definition of the derivative, to find the general formula dy dx for the derivative of the function 2x squared minus 3x. So here we can kind of start it off. They're asking us to do in the notation of dy dx, so I'm going to say dy dx like that. The limit definition of the derivative, if you recall, is f of a plus h, and I'm forgetting something here. Let's go ahead and, it's the limit definition of the derivative, so I have to say the limit as h approaches 0, and it was f of a plus h minus f of a over h. That was the limit definition of the derivative that we had from our last section of material and from what we're going to be looking at here. And whether you think of a as the input or x as the input, it's still an input. I think on the last slide where it actually gave it to you, the limit definition used x instead of a. But anyway, so let's go ahead and start, plugging this in. And this is something that you should be able to do if you understood what we were looking at in the last video, the last section of notes, is that we're going to kind of take the a and the inputs, and we're going to use them in the function that was given to us. And so the way that I have the function is I'm going to, we have to include the limit notation until we actually take the limit of something. So I have to keep including the limit notation here. But the way that I'm going to do that is I'm going to say 2, because that's the first coefficient that we have. And wherever I have the x, instead of, I wrote it as a plus h, but we'll just go ahead and put it as x plus h, because we're probably used to thinking of the inputs in terms of x. And that value has to be squared, because the x term is squared in the function. And then I'm going to say minus the 3, and I'm going to substitute the same thing for the x plus h, which is what's going in here. So all of this that we see so far, that is the f of a plus h portion of the limit definition of the derivative. And then we're going to subtract f of a, which in this case is just the function 2x squared minus 3x. Now remember, you're subtracting the expression, so you need to keep it in parentheses We're not just subtracting the 2x, and all of that is over h. Because what's going to happen is we're going to say, well, let me not short things. We're actually going to say, the difference of the a's. Well, the one input was x plus h, and the other input was x, so the difference of the inputs for the denominator of our difference quotient, x plus h minus x. But you see that the x's are going to cancel. That's why we just typically put the h in the denominator. So the limit as h approaches 0. And now let's go ahead and start evaluating this. So expand the expression in the numerator, the x plus h squared, and we're going to get x squared plus 2xh plus h squared. Distribute the 3, and we'll say minus 3x minus 3h. Distribute the negative, and I'll get negative 2x squared plus 3x, and all of that is over h. So the limit as h approaches 0 again. Keep writing the limit notation until you actually take the limit. And now at this point what we're going to do is, if you didn't do it already, some people are going to be able to distribute the 2 on the last row just by themselves, but that's just not how my mind works. I do the expansion, then I do my distribution. So here I'm going to say 2x squared plus 4xh plus 2h squared. And also in the numerator, what we're going to see is that here I have a negative 3x and a positive 3x, and those are going to wind up canceling out. So I don't need to write those anymore. So I have a minus 3h and a minus 2x squared all over h. And again, at this point, when we start moving on to our next row in our operations, we're going to start seeing some things that are going to cancel out. The 2x squared here and the negative 2x squared here are going to go away. And ideally, that's what we want. We want everything that's going to be kind of like an x value. Essentially, we want to be able to have everything in terms of h, so that way we have a common factor that can simplify with the h in the denominator. But when I do that now, I'm going to have the limit as h approaches 0. So what I recognize in the remaining stuff here, and let me just kind of highlight what I'm talking about in the remaining bits. Oops. I want my highlighter. Didn't mean to cross that out. In the remaining stuff here, everything is written in terms of h. So h is going to be a common factor, so I'm going to go ahead and just factor that out. So I'm going to say h here, and that'll get me a h, and I'm just kind of putting these in order of the biggest to the smallest, plus 4x minus 3, all of it over h. And so when we're done, now at this point you can see that the h in the numerator here and the h in the denominator here are going to simplify to be 1. So now at this point I'm going to go ahead and do my limit notation. I'm going to actually substitute the 0 into, now I can kind of just take the 0 and put it in here for h and see what I wind up getting, and of course that's going to be 0. So I don't need to write the limit notation anymore, and I'm going to be left with just 4x minus 3. And that is going to be the derivative of function f. So that would be, in this case, we're writing it as dy dx. And if that is the expression that we would use to find the slope at any point along the curve of the quadratic function that we started with for function f. That, of course, doesn't give you the slope of a tangent line itself. You still have to plug in an x number there to figure out what that value would be. But that is kind of just refreshing ourselves what we did last time with the limit definition of the derivative. So here on this next example, it's kind of asking you to do the same thing. Use the definition of the derivative to find f prime of x. So here I'm going to pause. I want you guys to pause the video and do example 2 on your own and see what you come up with. And here in a second, I'll put my answer up on the board or on the screen so you can see what I have. So pause the video, work it out, and then hit play again. Okay, so here is the work that I have for this example, again, where we're using the limit definition of the function. So they're using the notation of f prime of x for the derivative in this case. So I start off with the limit definition up at the top, just so everybody's familiar with it and knows exactly what I'm doing. So f of x plus h, kind of like on the last example, we have to put the x plus h anywhere I have an x term in my function. So from here to here, all of that is just the f of x plus h. And then let's pick another color here. And then for here, minus f of x, that's this bit here. So at this point, you go ahead and do your distribution and start combining any like terms. X plus h squared gives us x squared plus 2xh plus h squared. Then we distribute the negative for minus x minus h, and then again distribute the second negative, and we get negative x squared plus x. And recognize in the numerator, a lot of the x terms that are x's by themselves all wind up canceling, which is kind of what we want, because we want to have something left that's just in terms of h's. And so the 2xh plus the h squared and the negative h can have an h factored out, giving us h times 2x plus h minus 1. The h's in the numerator and the denominator simplify to be 1. And at that point, I can substitute 0 in for h to evaluate the limit. And I'm left with the derivative of function y, in this case, is going to be 2x minus 1. So now, moving on, we're going to take a look at what's known as the alternate form of the derivative. So the first one that we see here up at the top, that's the limit definition of the derivative, where h approaches 0 for the limit. Well, the alternate form of the definition is going to take the function that we had, subtract something where we're evaluating the function at, and we're going to say the difference of the denominators is going to be whatever x is minus whatever a is, and that is how we're going to evaluate this. So usually what we see here, this is usually going to give a function of some kind, like what we saw in the last examples. And usually this is going to give us a number, which would actually be the slope of the tangent line. And of course, it's provided that the limit exists for the function. But for these examples, yes, the limit is going to exist. So let's take a look at this example here, where we're saying use the alternate form of the derivative to find f prime of a for function f, which is the square root of 3x plus 1 at a is equal to 1. So here, let me go ahead and pick another color for things that I'm going to work out here. The alternate form of the limit definition of the derivative is f prime of x is equal to f of x minus f of a over x minus a. So in this case, they're showing us that a is going to be a 1. So that's what we're going to kind of be evaluating the function for. So one of the things that I want to know is what is f of 1 going to be? So 3 times 1 plus 1 gives us the square root of 4, which gives us a 2. So f of 1 is a 2. And that's kind of what we're going to evaluate in the function itself or in the problem itself. Okay, so that f of a that we're finding, which in this case is f of 1, the y value that we got is a 2, so that's what I'm going to put in the f of a spot. So let's start plugging in our numbers. F of x is just the function that was given to us, which in this case is the square root of 3x plus 1. F of a, in this case, is f of 1, so plug in the 1 to the function like I did here on the right, and I'm going to get a 2. And in the denominator, we're going to subtract x minus a. Now, x is just x right now, and a in this case was the positive 1, so I'm going to say x minus 1. Now, this is what we saw previously, and I am neglecting to put my limit notation here, so let me put my limit notation, because equals the limit as h approaches a in this case, which would be a 1. I forgot my limit notation here. Limit as h approaches a. Sorry about that. But let's go ahead and work out the problem. This is something that we saw to try and evaluate this. Of course, if you do the direct substitution now, you're going to get a 0 in the denominator. And what we did for previous problems like this to try to simplify it is we we took the conjugate of the radical expression. So the square root of 3x plus 1 in this case will be plus 2, and we're going to multiply that to both the numerator and the denominator and see what we get. So when I multiply through in the numerator, limit as h approaches 1, we're going to get a 3x minus 1 minus 2 over, we're not going to even bother to try to distribute here. We're going to keep everything in factored form. 3x plus 1 plus 2, like so. And combining the like terms that I have in the numerator, we're going to start to see how something is going to factor out pretty quickly. In the numerator, I'm going to get a 3x minus a 3, and I don't know why I'm putting parentheses here, over the x minus 1 times the square root of 3x plus 1 plus 2. And you can see in the numerator, we can factor out the 3 and I will say 3 times x minus 1 here over x minus 1 here times square root of 3x plus 1 plus 2. And we see here x minus 1 and x minus 1, those factors simplify. And I'm starting to run out of room here, so I'm going to kind of bring it up here a little bit just so I can have a little more space to write. And I'm going to say the limit of the function as h approached 1 in this case is going to be 3 over the square root of 3x plus 1 plus 2. And now we can start plugging in now we can actually substitute the 1 for the limit, so I can stop writing the limit notation, and I'm going to say 3 over the square root of 3 times 1 plus 1 underneath the radical plus 2. So I'm going to get a 4 underneath the square root, 4 plus, so the square root of 4 is a 2, so I'm going to get 3/4 for my slope. That's actually the slope of the tangent line. That's not the expression that will get me the slope like what we've seen by doing the limit definition of the derivative. The alternate form here, because we're already kind of evaluating it by taking that a value, in this case of 1, and plugging it into the function, this one will give us directly our limit or our slope at that point. So the slope of the curve at this particular function, when a is equal to 1 on the x-axis, will have a slope of 3/4 to be tangent to the line or to the curve at 1. And that's how we're looking at the alternate form of the limit definition of the derivative. One gives us typically an expression, the other typically a number. So moving on here, we see this table, and for one given point of A at f of A, they're showing that we're getting an instantaneous rate of change. X is equal to A, slope of the tangent line, derivative, X is equal to some number, and the limit definition of the derivative. These things here are generally going to be something referring to your tangent line. Here, the average rate of change over some interval is going to be the slope of a secant line. So that's what I would have written there, but the slope of the secant line. And of course, we're still doing a difference quotient that would just give us the slope of that particular secant line. So here I'm going to go ahead and do one of these examples. I'm going to go ahead and just ask you guys to pause the video at this point, because here these are both using the alternate form of the limit definition and the limit definition itself. And I want you guys to go ahead and pause the video and see if you can work these problems out based on the examples that I have already done for you. So when you're done, hit play again, and my stuff will pop up here in just a second. Okay, so what we see as we're comparing the use of the two types of limit definitions of derivatives. So what we have in A, this is where we have the alternate form of the limit definition. Now, of course, because they're telling us that we're evaluating the function at x is equal to 3, I want to know, well, what is the y value at x is equal to 3? So plugging that in is going to give me my 2/3. So f of 3 is 2/3. So that's what I use for the right side of the numerator in the overall difference quotient. So we have 2 over x minus 2/3, and all of that is divided by x minus 3. We rationalize the numerator by multiplying the top and the bottoms by 3x, and we wind up with 6 minus 2x over the 3x times x minus 3. And ideally, you're going to recognize that the numerator can be factored with a negative 2, giving us x minus 3 factors that simplify to be 1. So the limit, as we approach 3, in this case, the way that we've seen it, is going to give me negative 2 over 3 times x. So now we can do our substitution without having a 0 in the denominator. And so the slope, the actual slope of the line that's going to be tangent to the hyperbola at x is equal to 3 will have a slope of negative 2 over 9. Now in B, what we're seeing is the limit definition of the derivative. And in this case, because we know what we're evaluating it at, we're still evaluating it at x is equal to 3, the numerator on the right side does not have the x, or actually it doesn't have x at all in the numerator, or a in this case is the way it's written. So as we go through the arithmetic with this one, we should still wind up with the same value, because we're actually substituting a value for x as opposed to leaving x in the limit definition. So as you work it through, following the steps along, you can see again that we wind up with a slope of a tangent line to the hyperbola at x is equal to 3 will have a slope of negative 2 over 9. Now, just a little thing here. They're giving us the function of y is equal to 2x, so the derivative y prime would be negative 2 over x squared. And so you can see that if you took the 3 and you plugged it into the derivative, you're still going to wind up with that negative 2/9. Now, I haven't shown you how to get to this yet without doing the limit definitions and stuff, but we'll get there. Excuse me. So here, now what we're going to look at Here it's kind of just verbally kind of giving you some explanations. The slope of the tangent line at f is going to be equal to some value, x is equal to a. The instantaneous rate of change is the same thing, because the slope of the tangent line, the instantaneous rate of change, and the derivative are all telling you the same thing. And that's usually what we think of the derivative of a function being, is one of those three things. But the fourth one is saying that the limit of the difference quotient, nobody really thinks of it like that, at least not in my experience. So slope of the tangent line, instantaneous rate of change, or simply derivative, all refer to the same thing. So here, this next bit is asking you to do things with some colored pencils, where it's asking you to use a blue color and a red color. And it's asking you to identify some things graphically with the colors to see, is it going to be a slope, or is it going to be a length, I should say. And I'm trying to see how I can do this, because I know the way that I'm going to have to cut some things off. So I'm going to have to write 6 and 7 kind of on the right here, because I can't fit the table with the functions, or with the rest of the pictures that we see here. But let's just go ahead and start talking about it. Use the expression in column in column 1 is what it's referring to identify whether the expression there is going to be the length of a segment or the slope of a line that we see on the graph. Draw the representation using either a blue pencil or a red pencil. So here, f of a, that's a y value. Okay, so a y value here, this is what they're talking about, f of a. When x is a, whatever it is, what is y going to be? So this is right here, that is referring to number 1. And that is very much talking about a length. So I just put L for length. So the terminology here, as I'm saying, the value of f of x, meaning what's the output at x is equal to a. Now the next one, where it says f of a plus h, that's still going to be an output of some kind. So f of a plus h is looking at this bit here. This whole thing is talking about what we see in row 2. So this is still going to be referring to a length of some kind. So this is essentially the same, the value of f of, and in this case, we'll say x plus h, or no. The value of the function f at when x is equal to a plus h. So the third one, because we've already established that f of a plus h and f of a are both lengths, we can reasonably conclude that this is also going to be a length of some kind. And it's just the difference of those lengths. So, and I kind of messed up here. Let me clean this up. This from here to the x-axis, that's 2. So from here, this point to about this point here, because if we just kind of come across, it'll be about that point. From here to here, this is 3. That's row 3, the difference between f of a plus h and f of a. And that's exactly what I'm going to write here. It's the difference of f of x between x being equal to a plus h and x being equal to a. So h, that one's one of the easiest ones to see. H is right here. That is the difference between whatever x was at A and that small difference that we're including here. So this is row number 4. That's also going to be a length. Generally think of this, the difference between two points along the axis here. We are looking at that as displacement. Or you can think of it as the difference between A and A plus H on the x-axis. But I'm not going to write all that stuff down. So 5, here, this very much should automatically trigger the fact that this is going to be a slope of some kind. Because what we're seeing in 5, that is the limit definition of the derivative, which is the slope of a tangent line. So here, 5 is, in this case, it's kind of referring to this bit here, where we're saying the difference of f of a plus h and the difference, and f of a. So this bit here is representing row number 5, and this here is kind of an average rate of change. Of the function on the defined interval of a to a plus h. Now 6, which kind of got cut off on my screen here, okay, so we'll do 6 here. 6 is giving us the limit as h approaches 0 of f of a plus h minus f of a over h. This is the limit definition. The 5 is just a difference quotient. This is the limit definition of the derivative. That's actually the slope of a line tangent to a point. In this case, we're talking about point A. So 6 is going to be the slope of a tangent line. So 6 is definitely going to be a slope. Come on, slope. And the terminology for the slope in this case would be an instantaneous rate of change of the function at x is equal to a. And that one is going to be kind of right here. This guy right here is what row 6 is going to be. And the last row, 7, where 7 says f prime of a, the derivative of a. Well, again, derivative is very much a slope. Slope of the tangent line, instantaneous rate of change. Still talking about slope of some kind. And this is really the same thing as what we saw in 6. So the limit definition of the derivative and the derivative all produce the same thing. Now, last thing that we're going to take a look at here is talking about understanding a derivative symbolically. So here it's asking you to extend your knowledge base for operations so you can recognize when we're going to have different things, there's functions, properties, processes, and whatnot. Here they're asking us to kind of decompose or essentially work backwards from what we have. And what we're seeing in these examples, and I'm going to do A as an example, and then I want you to pause the video and then you guys do B. So we know that the derivative is the slope of the tangent line, is the limit definition of the derivative. They're all the same thing. Or we can see the alternate form of the limit definition of the derivative. So what we're being asked to do in example 6, it says we want to be able to identify what is the basic function, y is equal to f of x, and what is the input number, what is x actually equal to in that case. Well, in this case, here, the function, let me pick something right with here. So in A, the function, it's asking us, well, what is the function here? So y, in this case, we're just kind of looking at this. This is going to be the square root of x. That's what the function is going to be. So now what we're being asked to do is, what is x going to be equal to? Well, x is going to be equal to whatever kind of the input number is. And in this case, what we're kind of looking at here is that 4. That number that you're plugging into the function, that is going to be what x is, or what c is in this case. So here I'm going to say that x is equal to 4. And that's really all we're kind of looking at for this example. So go ahead and pause the video and you guys try to do B, and when you're done, hit play to see what my answer is. Okay, so here is B worked out for you. Here, the basic function that we're seeing from the difference quotient is going to be e to the cosine of x power. And in this case, the input value that you're looking at for x, or c, however you want to think of it as, is pi. So that is how we're kind of looking at those backwards from the difference quotient to identify what would the basic function be and what would the input value be. And again, here we're looking at the same kind of concept as h is going to approach 0. And I'm going to do C for you again, and I want you to try doing D on your own, or pause the video now and try and do both of them on your own. But C in this case, the basic function here is going to be y is equal to tangent. Now this whole thing, we can kind of think of the parentheses themselves as like what we're plugging in for the function, like theta or x or whatever. But this 2 that's in front of it is going to be part of the basic function also. So this will be 2x or 2 theta or something like that. So that's the basic function. And the number that you're actually substituting into it is the 2. So x or c, whatever you're thinking of is, will be 2. So go ahead and pause the video if you haven't already done so and work out D. Oh. Okay, I had to rewrite C. I did something and erased my work there, but now looking at what we have on D, D, I rearranged it so that way it's looking more like the difference quotient that you're kind of used to seeing by now. So the basic function that we're looking at is the natural log of x, and the x value that we're using in this case is 6. So last examples here, these are going to be slightly different than the original functions. It says these examples differ because the limit, if you're paying attention to, doesn't approach 0. They're approaching a specific number. So looking at, still looking at the same thing, what is the function going to be that we're looking at? The function you can think of is, in this case, going to be y is equal to just the parentheses x minus 1 squared. That's the basic input function. And x is given to you for the limit. X in this case is 3. And the one on the right is going to be y is equal to the cube root of, let's see, that's going to be x minus 6, and the y, or the x value that we're looking at again is given to you here to be a negative 2. Okay, and that is going to bring us to the end of our second lesson in derivatives and how the limit definition and the alternate form of the definition are going to be used to either create the expression for the derivative, identify the slope of the tangent line at a certain point, what the different types of notation for derivatives are going to be, and how you determine what they are, either algebraically, graphically, or symbolically. But thanks for watching, guys, and take care.